multi-instanton solution. Okay. And so yesterday we saw that we could write an ansatz or whatever for this thing by starting with something which G inverse d mu G other way around, and introducing some function only of the radial coordinate in front of this. I did not prove anything, but I said that the following thing is a solution, and that was r square by r square plus this thing. And we were doing so this follows from the Euler-Lagrange equation, and this is something which will be there in your assignment for you to check, but we can look at some look at this solution in some detail. And so if you look at what this looks like, so where r square was just tau square plus x a x a. So the point here is that we could always do the thing following thing. So this thing can be generalized a bit, is to just say wherever we saw x c, we replace it with x c minus some x naught or some x bar c, and tau by tau minus some tau bar. Okay. And if you, and of course r square will also get shifted appropriately, so r square will also become tau minus tau bar whole square plus okay. So once you do this, I mean it's not too hard to see that this will continue to satisfy the equations of motion, and these things, now there are 3 parameters, so rather 5 parameters. So we start, so this is 1, this is 3, and then there is the size which is 1. So we have 5 parameters. Okay. So I did a quick count for what should be for a 2 instanton solution by intuitively saying that fine. So here the interpretation for x bar c and tau bar, or tau bar, let me write it in the other way, tau bar and x bar c, as these are location of the instanton, and this is the size. So this is how we understand the 5 parameters. I should also give you a 0 . So you will be verifying all these things in your assignment. Okay, so this should follow more or less from this kind of an answer. Sorry. Okay, and yesterday we missed out a minor factor when we worked out the energy or the action for a k instanton. That means, by this I mean instanton number is k, or the winding number is k. We worked it out to be 8 pi square times mod k, but actually in the action there should have been the coupling constant square, E square or G square, whatever we want to call it. Okay, this is just an overall multiplicative factor, so it does not change any of our discussion, but this is what it should be. But the question is, how many parameters do we expect for a k instanton solution? Okay. So, roughly here we had an interpretation, this breaks translation in space and time, and there is also the scaling symmetry which is broken. There are other symmetries which might lead to gauge transformations. So, they are not they are still a symmetry of the solution, even though it might change the form, you can show it is a gauge transform of the same thing. So, the idea here I did, let us do the counting for 2 instantons. So, I said let us think of 2 guys separated widely, and then the thing is then we would have 5 parameters for this guy, 5 for this, but the key point is that out here there is always a global SU2 transformation. If you want to keep that, so you can count, so I can go ahead and act on this by an SU2 transformation and I will get something else. So, that is 3 more parameters. Yeah.
Will there be parameters corresponding to boosts?
This is a Euclidean this thing. So, you would talk of SO4 rotations. SO4 rotations is not really broken, it is a gauge transformation. Okay. So, there are no more there are no more parameters out here. Okay. So, the point here is that so you would have thought so this thing and you except the point I made is yesterday is that there are 3 more parameters because there is a relative gauge transformation, relative SU2. So, if you take this, this had an SU2 and global thing which I could have done. Similarly, I could do with this, but then the overall thing can be removed. So, plus 3 for the relative SU2 freedom. Okay. So, this counting will give you 13 parameters for k equal to 2. Okay. So, now you can see that what we have another way of understanding this as 16 minus 3, it is simpler to associate. Instead of saying 5 parameters with a 1 instanton solution, you say that there are 8, including you treat the SU2 as extra freedom. So, and overall we subtract an 8. Okay. So, you can see that that is kind of fruitful because when we talk of k instantons, for every instanton we will count 8 and then you subtract a 3. Okay. So, the claim based on this thing is that the number of parameters okay, by the way these are called sometimes they are called moduli. Okay. The reason they are called moduli is because you can change these things without changing in this case the action. In the case of solitons you can think of them as not changing the energy. Okay. So, the number of free parameters for the k instanton solution is 8k minus 3. Okay. So, now the thing is why did I write it as a claim? Is there a way of proving it? The answer is very nice, the answer is yes, there is a method of proving it. So, what you do is you take if you have some continuous parameter, obviously you can if you choose a solution that corresponds. So, let us think of this is your parameter space and you picked your solution at some these things. So, for instance here I could have said that I have chosen rho to be some number and the location to be the origin. So, it does not look like those parameters are visible, and how did I here I was because I had some geometric insight I was able to bring these things back into the problem. Okay. But that is because this is a 1 instanton solution, but out here the question is it easy to see these 3 parameters, we do not know. Okay. So, what you want to do is to so if you are given a solution you want to ask how many directions flat directions are there. Okay. By that I mean flat in the sense the things which do not change the action. So, what you do is you ask for what are called 0 modes of the equation. So, you look at the equation of motion, in this case it is just you could write the equations as d mu f mu nu equal to 0, and the Bianchi identity is just d mu star f mu nu equal to 0. So, these are the Euler-Lagrange equations and the Bianchi identity. So, what you do is you take, so you start, so you are given a solution. So, let us say we are given a solution a mu 0, to this you add a small perturbation. So, you say that, okay. So, in other words, what I have in mind is, suppose we did the so here we start with let us focus for instance on the location. So, what we have out here is that initially we set the location at the origin and I want to shift it, but I want to shift it by a very small amount. So, then I can think of the position x bar c as small and expand it as a power series in x bar of c and keep only the first order piece, okay. And that piece, whatever is the coefficient of that, I can call that delta of a mu, okay. And so that should continue to be a solution of this equation. So, it is true all orders, but to count for just getting the number counting is sufficient to go ahead and plug things in here. And you can see that and if you think so we just need to substitute this here and keep terms to order delta mu nu. So, a naught already satisfies the equation. So, the first order piece will look very easy. So, this will just satisfy something like d naught of mu. So, you take times d mu naught of a delta a nu, or yeah, I think something like this. Okay, so, what I have in mind is, suppose let us look at what I am doing here. F mu nu would have been d mu. So, I have a whole bunch of terms. So, let me write out this term. Plus there is the other the quadratic piece, but just look at this. So, if you are going to ask how does this look, you can see that to leading order, so this will just become f naught mu nu plus this piece will give d mu of delta a nu minus d nu of delta a mu, okay. Now, what about the other piece? The other piece would have been something like 2 a's. So, it will be a mu a nu kind of piece, maybe there is an I, okay. This is the piece. So, here now you can see that if I want to linear order, the linear order here would just become replacing one of these with a naught and the other with this thing delta a. So, all that will add up and give you some sort of a term which will look like this. So, you have to find solutions to this kind of an equation. So, this looks like some adjoint valued scalar kind of thing with some equation which is coming from the given Euler-Lagrange equation. So, you want to solve it and you ask how many independent, it becomes a linear equation. So, you can ask how many independent solutions it has, okay. And that is the way you go about, and you can convert this into a mathematical problem. If this is a nice well posed problem, you can actually you can do the counting, and in some cases it gets mapped to what are called index theorems, and you can do the counting and then you can prove that this is correct, okay. I am just giving you an idea how you go about proving this, because this is just hand waving. I could have missed something, okay, but it is like at least you can go back, do the fancy math and then come back and see if you can physically understand it, and this is a nice picture, okay. So, but now the question is how do we go about writing a solution which has all these 8k minus 3 parameters, okay. That is not something which we will do, but what we will do at least is to write a slightly simpler solution where we will get, instead of 8n we will get 5k, instead of 8k we will get 5k kind of this thing. That minus 3 etc. is not so, it's not a big deal. So, let us so for that I will rewrite this particular thing in a slightly different form. So, I will define something called alpha mu nu, Okay, so x square is what I called r square there, maybe I should call it r square. No, I will call it x square, you will see why, because I want to shift and things like that, then it thinking of it as x square is sensible, and of course mu nu goes from 0 1 2 3 4 1 2 3, okay, and f mu nu for this looks like 4 I rho square okay. So alpha mu is just identity, alpha 0 is identity, and we have seen this combination quite often. For instance, when we wrote x a, we combined it with the Pauli and the identity matrices to write the most generalized U2 element. So you can see that this is has that thing, and define alpha bar to be alpha mu dagger. So that will be identity dagger is this, but just change the sign here. Okay. So define alpha mu nu okay, yeah, okay. So the claim here is that alpha mu nu is equal to star alpha mu nu. So it's self dual, okay. So it does not take a lot of work to just plug these things in and see that you get something which looks exactly like this. Okay. I will not swear that the signs are exactly the same or whatever, okay, but this is what you get. Okay. So the idea here is to, so the ansatz, I guess this is Etouff's ansatz for multi-instanton, is to look at this thing and say let's do the following. Let's choose a mu to be I alpha mu nu times d nu of some function of f. Okay, this is the ansatz, and then you can ask what is the equation of motion for f, and that is very nice. The equation of motions imply box f. Box f of x equal to 0. This is a 4-dimensional box. So by that I mean this is kind of very nice, it is very interesting also. What you started out, your actual equations of motions are non-linear, okay, but what is coming out of this is this, after this ansatz, is that you are getting something linear. It tells you that superposition works, okay. And so now you can see that I can go ahead and just sort of roughly add one instanton solutions, and here is what one does, and so you can, so we can choose f of x to be say 1 plus this 1 x minus, okay. So straight away you can see that there are these 5 there are 5 parameters for out here, one for the size location, 4 from coming from the location, and this is the size, okay. So you get 5k, so this has at least 5k parameters, okay. So the nice thing is that it does not capture all these things, but it at least captures some of the, I mean, and you can see what are the missing ones in some sense. It is the relative gauge stuff, but you can also see that it is not so simple to it is clear that this kind of ansatz will not I mean there is not much tinkering you could do with this to get the other ones, the relative ones. It is not so simple.
That is why superposition works.
Huh? No, there is some underlying integrable structure in the self-dual Yang-Mills theory in the equations. So it is related to that. I would not say that I mean that is why, okay. It is much deeper than that, okay. So, but it is quite it's kind of nice that there is a simple way of understanding the solution, and you should know that we are looking at. So, this is Laplace's equation in 4 dimensions. You know that it is 1 upon r it is 1 upon r, the green function is 1 upon r in 3, it is 1 upon r square, okay. So, obviously this thing has singularities. You can see if I look at 1 by its sum by r square, right. So, it will have singularities at those locations of the instantons, but beyond that it is okay, it satisfies that equation, okay. So, this is a solution due to 't Hooft, and the more general thing I was thinking about it, I feel that it is a little bit complicated, but when I talk about dualities there is a nice geometric way of understanding the ADHM construction. So, the ADHM construction gives the full 8k minus 3 parameters, okay. So, this is just a remark. So, all these things you will be working out in your next assignment, so that you know how the algebra works out. Okay, give the most general solution, okay. And so this so coming back to this, there is this funny space which is 8k minus 3 dimensional space. So, in some sense let us forget about the overall 3 and think of it as 8k dimensional space, okay. And so this space is called such as this space the space of parameters is called the moduli space. Of in this case k instantons. Okay, so we can just write something like this mk, okay. And remember, now I have gotten rid of that minus 3. So, this dimension of the space mk equal to 8k, okay. This space turns out to have beautiful properties. Again, it follows nicely from this construction. It is a special space, it's called hyperkähler. So, a Kähler manifold is some first thing is you can go so this is counting in reals. So, a real manifold you can go to you can put some you can work in complex coordinates. There are some consistency conditions. So, a space goes from real being a real space to a complex space, but Kähler is very special. It's a space which is both complex, Hermitian, and it is also has a symplectic structure. So, it can also be like a phase space, okay. Hyperkähler is has much more structure. So, there is a very special kind of this thing. The hyperkähler manifolds necessarily have dimension which is multiples of 4, just as complex manifolds necessarily have dimensions which are multiples of 2. Obviously, an example of a non-complex manifold is R. You can there is nothing to complexify even. R2, yes, you can make it into one complex. R3 again you cannot, okay. So, that way hyperkähler spaces are so again there is one more reason to this thing, but this so the 8 dimensional one is actually very easy to understand. So, 8 dimension, what were the parameters? There was an R4 and okay, and then we had the SU2 is just an S3 and the size is like a radial direction. So, you can see that the S3 and the radial direction can combine and become an R4 with the with if you wish the okay So it becomes actually a second R4, but actually there is a little bit of discrete subtlety that space becomes R4 with a Z2. Okay. The center of SU2, which is a Z2, does act trivially on the solution. Okay. So the moduli space is, so it's don't worry about this is a technicality, but all I am saying is that the moduli space is 8 dimensional, it looks like 2 copies of this thing. Okay. This Z2 means there is an identification. Okay. Beyond this I will not yeah, okay. So in fact there is should I say more? I shouldn't, I will just stop here. Okay. By the way, I got the number of pages wrong in ADHM paper. I said 1.5, it is actually 2 with a bit on the other side, references coming on the other side. So it was 2 pages which all these things were done. So we sort of motivated instantons by looking at tunneling in quantum mechanics, and so we looked at the double well example, and that is where we started, and we saw that the kink soliton was related to this gave the tunneling amplitude, if you wish. Okay. So there was one at minus a and one at plus a, there were 2 vacua, but of course we know quantum mechanically, because of tunneling, the true ground state is neither of these 2, but some linear combination, and so just let us call the, so in quantum mechanics let us just call plus and minus as the 2 solutions. No, yeah, leave it there. Should I call this? No, I will just call it plus a and minus a. So this is a solution which is localized at plus a, and this thing the other one is localized at minus a, and we know that the true ground state, so classically this is sort of capturing what we would have done classically. It has 2 ground states. Okay. One is at x when it is at x equal to minus a. So I am just saying, well, let us think of some harmonic approximation, and you can think of this as a Gaussian centered here as an approximation, and this as a Gaussian centered at OT, or the other way around. Okay. This is centered here, this one is centered here. Okay. But the true ground state is neither, is the even guy, and so let us say the harmonic approximation, let us say that the energy would be some half h cross omega, where omega is determined by the curvature of the potential out here, the second derivative evaluated here, that would be the harmonic approximation. Okay. But the true ground state would have would be a linear combination, so it will be something, in this case because of symmetry it will just be this, a good guess would be something like this. Okay. And the energy would be minus something. Okay. And this is due to tunneling. So one way of saying this is that, suppose, so the energy would be something like half h cross omega, half h cross omega, and the off diagonal terms would correspond to the tunneling contribution. So, and because of symmetry this will be some number, and this will be actually determined by the action. So it is typically of the form of some constant times e power s naught, and this is also the same constant e power s naught. Okay. And so this thing will be, so there will be 2 this thing, so e plus minus, which will be minus or plus, let us stick to the ground state, some constant times e power minus s naught, where s naught is the action evaluated for this guy, for the king soliton for instance. That would be the semi classical estimate for this thing. But suppose we have several infinite, suppose we have a periodic potential, Okay. So, then the number of ground states are infinite, and so obviously you can tunnel from one ground state to any one of this things. So, there will be many different kinds of instantons. Here there were only two kinds of instantons and anti-instantons, but here which would be of 1 and of taking you from minus a to plus a. So, if you have a periodic potential say of a sine for instance, and let us say that this is 0 a, one full thing should be an a, 2a minus a, so on and so forth. So, I have some lattice spacing. So, my potential V of x plus a in one dimension is equal to V of x. Okay. So, in quantum mechanics you must have heard of Bloch's theorem, okay, which we can view again from a different viewpoint. This is a system where the potential breaks translation symmetry, right. So, momentum is not conserved, but it is broken down to this discrete group, and so momentum is conserved modulo this thing. So, so Bloch's theorem tells you that you could write the wave function psi of x plus a will not go to itself, but it will go to something up to some phase times psi of x. That is your symmetry in the, and this theta is usually written, theta is usually identified with something called k times a, and k is called the crystal momentum. But k is only defined modulo 2 pi over a. Okay. But the key point here is that there is a whole so this is a characteristic of the wave function. So, you could say that we can say that it carries psi of theta, this is this thing. Okay. So, theta going from 0 to 2 pi over a or minus pi by a to plus pi by a, which is called the first Brillouin zone. So, k will take values within that, then you will not have this mod 2 pi over a is taken care of, and but the point is that you started out with a discrete set of ground states. So, what this would tell you is that there is a theta set of vacua in some sense. So, I just identified this wave function with some theta, it is a continuum. Okay. Out here we just got two vacua we got, okay, and it was just plus or minus, and the energy of this thing goes like some alpha plus some beta of some theta or cosine theta, maybe, I do not know, something like this, depending on the details of the potential, etc. So, now let us come back to our instanton solutions. So, the situation is exactly like this. We have infinite number of classical solutions, all which have 0 value, okay, and how is that? So, just take a mu to be pure gauge, but with winding number n, like we did last time. Each one of these things will give its pure gauge. So, f is 0 and the action is 0, E, B, everything is 0. So, these are really, so the point here is that pure gauge solutions are indeed ground states, true ground states of the theory, and there are infinite of them. And so, instantons which we were constructed, you can think of them as, so an instanton solution, a k instanton solution interpolates between ground state n and n plus k. Right, it need not be 0 to k, it can change, it should only change. So, it is exactly like this, I could a 2 instanton solution can take you from this vacuum to here, but it could also do this, it could take you from this to here. Okay, so in that sense it parallels exactly this thing, and it tells you that you have theta vacua. So it suggests that the true ground states or the true states, if you wish, eigenstates or whatever, yeah, true ground states will be the analog of the theta, what we will call theta vacua or whatever, something like this. Okay. So is this clear? Okay. Now a related fact actually related to this is the fact that if you go back to the action, so if you were looking for constructing an action for Yang-Mills, in your assignment I asked you to write out the most general 2 derivative terms involving the gauge field. So the key point is that there are exactly 2 kinds of terms. One is our normal term which we had written, but we could have written something like this, and what did we say this so the argument will be that this is a total derivative, and so it does not usually you say that it does not change the equations of motion, it does not affect the equations of motion. So you can add such a piece, it will not change the equations of motion. So this is a total derivative, we know this is equal to some d mu of omega mu, it is a total derivative, but the point is so we could try to write an action which has such a term, and let us say we did something like this. So we choose the Lagrangian will be 1 upon 2 e square okay, plus I theta times the instanton number, I will put that. So I will just define things. So that was theta by 16 pi square, right. There is a half in the definition of is that correct? Yeah. So I write this. So you could write and I put an I out here. Okay, so this is the kind of action you could put in, and you can ask if you have an instanton background, how would the action change? And what you will see is that suppose, so you ask for a transition amplitude in the without this term it would have been just the instanton action, but so for this we have to, so tunneling or transition tunneling amplitude, if you want to work out, the tunneling amplitude would have been just S minus instanton 8 pi square times the instanton number upon E square. This is the contribution that we would have got by from the one instanton this thing, okay, and higher instanton terms will get will have further suppression. So this is the one instanton contribution, but there are 2 such contributions. If you add such a term, one of them will give e power I theta and the other will give okay, plus terms which are suppressed. So, higher instanton terms. So, this is a saddle point. So, in general I should point out that when you have when you are doing the saddle point evaluation, you have to sum over all saddle points, and you should remember that every multiple instanton solutions also give you other saddle points. They are as good solutions to the equations of motion. So, in principle you have to sum over all of them. So, here I am doing the Euclidean thing. So, you can see that the 2 instanton guy will come with a 2 out here, which is exponentially suppressed relative to this. So, I am writing out the most dominant term, and this so this will give you like a cosine theta, which will be a which is a contribution from this thing, this term. This term is actually interesting. This factor of I does not go away when you go to Euclidean space. Okay, the reason is the following, is that so how would you, so what would happen is that you would have some dt and yeah, so let us look at, so there will be a d cubed x. First let us do the normal term f mu nu f mu nu. So, what happened last time when we did the Wick rotation out here, we saw that this was nice, and this took it was e square minus b square, and so yeah, so what happened is that the b term flipped sign, okay, but the I which came from here remained. So, dt went to minus I d tau, okay. But if you look here, a typical term, the term here would be f 0 1 f 2 3, this kind of term, okay. So, there will be an I coming from this f 0, which will get rid of this I, okay. So, such a term, so what I am trying to say here is dt of this thing will just go to d tau of the modified f 0 1 f 2 3, because the I coming from this gets exactly cancelled, this has a d by dt if you remember, okay. So, this goes away, so it just goes, it remains the same, okay. So, this factor, so yeah, so this when I put it in Euclidean space, it just gives you this kind of a phase, but when you go back even to Minkowski, this remains, this factor of I does not go away, okay. So, this is a pure imaginary, it gives you a phase, this thing. So, in some sense this captures this kind of phase, okay. So, yeah, so the upshot of this is that the most general vacuum Lagrangian you would write would be something like this, but like I mentioned, this will not change the equations of motion, it is a total derivative, okay. So, equations of motion will be exactly whatever we wrote earlier, okay. And but there is also a nice complexification it causes, so 1 upon 2 e square. So, you could define, I am going, oh I have a tau now, this is normally called tau, what should I call it, okay. You define lambda to be 1 upon, sometimes it is written 4 pi you put here, 4 pi upon e square plus I theta over 2 pi. You just define it this way, and so this will give you a this is a complexified then this action has a can be written as a real part of a complexified f, okay. So, how does that work? Yeah. So, how so you define something which let us define f mu nu. So, let me define something called g mu nu to be f mu nu plus I times I am working in Minkowski here. So, this plus I comes, so I am taking the analog of the self dual combination, and G, let us call these things I guess G plus minus to be this thing. So, up to factors you can just write this as lambda G mu nu plus, now I am writing this from memory. So, I think this is the thing, plus complex conjugate. If you write this out, okay, G mu nu plus this thing plus complex conjugate, then you will, what you will get is this action with a complexified coupling. Okay. And so, this in fact this combination is very natural in supersymmetric gauge theories. This is how you get it. That is how. So, this appears in supersymmetric, something which we have not discussed, but okay. So, I just want to conclude about, so one thing to mention something about u1. We saw that pi 3 of u1 was trivial. So, there are no instantons for u1. Okay. So, this is something we know. So, when G equal to u1, since pi 3 of u1 is 0, there are no instantons. Okay. However, there is a deformation, however there exists what is called a non-commutative generalization, okay, of u1 gauge theory, okay, which basically says the basic fields do not commute. There is a theta parameter which measures non-commutativity. So, it is like an H bar kind of thing. So, I do not want to get into details, but all I am saying is that there is a parameter called theta. So, there is a family of, if you wish, non-commutative gauge theories with this parameter theta. Theta equal to 0 is a commutative limit, but if you switch on a theta, this theory admits instanton solutions. Theta is a real parameter. Okay. So, this is actually a very this might seem like a very trite observation, why do we care about these kind of theories, but like I said that the ADHM construction has a very nice realization, geometric realization in string theory, and there was a puzzle which came up, which in the geometric picture there should have been it sort of implied that there should be an instanton for u1 gauge theories. Now, there are two ways to think about it, that is total nonsense, and the persons who proposed it were actually given quite a bit of flack. They took quite a bit of flack until it was realized that actually there is a slight deformation, and so once you do that thing, so the theta theory has instantons, and it resolved a very important puzzle. Okay. Because I might be discussing a pictorial way of understanding instantons, and that time we will see this come back. So, I am finishing with this comment that there is a u1 theory which is a slight deformation of normal which admits instantons. Okay. So, by instantons I mean finite action solutions, etc., etc.